Now this should really give you something to think about. Just how far should you be able to see, and in particular objects from the bottom up? How much should be visible? To do this, we need to calculate the drop in the ground with distance. This is important and is fundamental in understanding that not all is as we have been taught. We can see too far, and we can see far too much detail of an object at distance. But how do we know this is true? Hence a mathematical formula to calculate the drop in Earth's curve with distance. So the question is, at what distance should the curve of the Earth, if it is real, hide what is behind it? Now, beware people talking about refraction. For globe believers would make you believe you can see behind a solid brick wall due to refraction. So where is the curve? And to work that out, we calculate the horizon drop. Here is a representation of the surface of the Earth. This is something you would never have been taught in school. Let us draw from the centre to the surface. Now, that will be the radius of the Earth. And the radius of the Earth is 3,963 statute miles, as we are told. So we know this distance A equals 3,963. Now, when you're sitting or standing on the Earth and you look straight out, our favourite word, drawing a tangent, you can't look over here because you'd have to look straight through the Earth. So all you can do is look out at 90 degrees to the Earth's surface, and we'll call this distance B, because now we want to work out what would be this height. This will be the drop with distance. So we'll call this whole length C, and this is a drop in the Earth's surface as you look out. Now, for ease of working things out, we'll say we want to look 10 miles. So B equals 10. So the question is, if you look 10 miles across the Earth, what will be the drop in the Earth's surface? And we have here now a right-angled triangle, which brings us to Pythagoras. And Pythagoras says, with a right-angled triangle, that a squared plus b squared equals c squared. This is one of the basic formulas of trigonometry. So this distance squared plus this distance squared equals this distance squared. So we can work it all out. If this distance A is 3,963 and this distance B is 10, then adding the square of both equals the distance C squared. And to work this out, all we have to do is to square root that and to square root that. And then we have 15705,369. Well, that's a difficult number, but this is 15,705,369 plus 10 squared, which is 100, and that equals c squared. So if you now square root that to equal c, it comes out that c equals 3963.0126. Now, what do we do with this number? Well, we know that the distance c, which is the radius of the Earth plus the drop, equals 3963.0126. But we know that this distance from here to here is the radius of the Earth, which is 3,963. So if we take 3963 away from the 0.0126 statute miles, it equals the drop. And we're almost there now, because all we have to do is to change that into feet. And we have here a conversion formula. 1 statute mile equals 5,280 feet. So 0.0126 of a mile equals that figure times 0.0126, which equals, wait for it, 66.6 feet. Therefore, the drop with 10 miles distance is 66.6 feet. Wow. Oh dear, Where have we found 666 come up before? Remember things like the tilt of the Earth, which is set at 23.4 degrees, which from 90 degrees is 66.6 degrees. And we're told we're travelling around the sun at 66,600 miles per hour. And 666 comes up everywhere. It's a lovely figure used by Satanists and Luciferians. But for now, this is what we've got, that the drop in the Earth horizon at 10 miles is 66.6 feet. This means that any object that is less than 66.6 feet will not be able to be seen from the surface of the Earth at 10 miles distance. We can do some mathematical jiggery-pokery to produce a general formula for the Earth curvature. The Earth's drop is 8 inches per mile squared. We have already established that at 10 miles the drop will be 66.6 feet. Here is a table showing some other figures. On looking at this table, I want you to understand a very important point. The drop is not linear. This means that if you double the distance, you do not double the drop. The drop is much larger. For example, in the table, a distance of 5 miles gives a curvature drop of 16.6 feet. Now, if you double the distance to 10 miles, it does not double the curvature drop. No. A distance of 10 miles does not give a curvature drop of 33 feet, but of 66 feet. The drop gets progressively steeper with distance. I should mention that this equation does not work out for all distances, but is a very good approximation for up to 500 miles. It's certainly good enough for everyday distances and sightings, and it should really give you something to think about.